Hi everyone, this is Mrs. Hanson. This is lesson 2-4, Zeros of Polynomial Functions, video 2.4.5 and 2.4.6. Our learning target for today will be for students to be able to use Descartes' rule of signs to describe the possible real zeros of a polynomial and find a polynomial function given its zeros. Okay, so Descartes' rule of signs is a key concept. And if we have a function f of x that's a polynomial, right? So we talk about a polynomial being either a quartic function, a cubic function, a linear function, a quadratic function, or you could have a degree 5 polynomial, which your highest exponent is 5, or anything higher than that for a degree. So, we have a polynomial function with real coefficients. Then there's two possibilities here. The number of positive real zeros of f is equal to the number of variations in sign for the function, or less than that number by some even number. Okay, so we'll take a look at that in a minute. And the number of negative real zeros of f is the same as the number of variations in sign of f of negative x, or less than that number by some even number. So the main point of Descartes' rule of signs is to look at a polynomial function and be able to determine, using this rule of signs, how many positive real zeros it could have and how many negative real zeros it can have. And remember, the word zero is the same thing as an x-intercept on the graph. So I'm looking for how many times is it going to cross the x-axis on the positive side, and how many times is this polynomial going to cross the x-axis on the negative side. So we're going to go ahead and look at this. The thing is, we have to look at for the positive real zeros is, again, the number of variations in sign of the original function, and then we can decrease that number by some even number, and the number of negative real zeros of the function is the same as the number of variations in sign for f of negative x. Not f of x, but f of negative x. And I always remember that because we're finding the negative real zeros. So we're going to substitute negative x into the function, simplify, and then count the number of sign changes, which we count the number of variations in sign, and it could be equal to that or less than that by some even number. Alright, so we are going to apply Descartes' rule of signs for this polynomial. It says describe the possible real zeros of the function f of x equals x to the fourth minus 3x cubed minus 5x squared plus 2x plus 7. Now, what we're going to do is we're going to start out by looking at the original function, f of, we'll call this f of positive x, because x right here is positive. And if we look at the original equation, the first term is positive x to the fourth minus 3x cubed minus 5x squared plus 2x plus 7. And if we look at this, starting with the first term, we have a sign change, right, moving from the first term to the second term, because it goes from a positive x to the fourth to a negative 3x cubed. We change signs because the first term is positive and the second term is negative. So we have one sign change. Now, if I move from negative 3x cubed to negative 5x squared, I do not have a sign change because we have a negative and we move to the next term and it's still negative. The next term is negative as well. So, anyways, we won't count that as a sign change because both terms are negative. When I move from negative 5x squared to a positive 2x, we do have a sign change. So that is my second sign change. Again, the first sign change was from x to the fourth to negative 3x cubed. And when I move from a positive 2x to a positive 7, again, we do not change signs because we were already at a positive here, and the next term is also positive. So we have in the original function two variations in sign, or two sign changes. Thus, the number of positive real zeros of f of x is going to be either 2, because there's two sign changes, or we decrease this quantity by an even number, and if I decrease 2 by an even number, I would get 0. Because if I'm going to decrease 2 by an even number, I would decrease it by 2, because 2 is an even number. And so therefore we either get 2 or 0 positive real zeros. So if I graph this polynomial f of x, it is either going to have 2 x-intercepts that are positive or none. And that's what I'm saying right here. Okay, so we now have to describe the possible number of negative real zeros. And we do that by first finding f of negative x, because again, we want to find the negative real zeros, and to do that, I evaluate my function at negative x. So what I get is negative x to the fourth minus 3 times negative x cubed minus 5x squared. Oops, take that back for a second. I need to substitute negative x and then square plus 2 times negative x plus 7. Now, I want to go ahead and I'm going to take negative x to the fourth. So negative x to the fourth is really negative x times itself 4 times. So I get negative x times negative x times negative x times negative x. So what that really gives me is a positive 1x to the fourth. And here, when I move to the negative x cubed is negative x times negative x times negative x, which really gives me negative 1x cubed. However, I'm going to multiply that by negative 3, which gives me positive 3x cubed. And if I have negative x squared, that's negative x times negative x, which gives me positive x squared. And then again, I'm going to multiply that by negative 5, so I get negative 5x squared. If I multiply 2 and negative x, that gives me negative 2x. And then obviously we just have the plus 7 on the end. So, in order to determine the possible negative real zeros of this function, I am going to count the number of sign changes in this equation here after I've evaluated for negative x. So when I move from the first term to the second, I move from a positive term to another positive term, so I do not count that as a sign change. When I move from the second term to the third, that is a sign change because it goes from positive to negative. When I move from the third term to the fourth term, I move from a negative to a negative, so I do not change sign. And when I move from the fourth term to the fifth term, here, I move from a negative 2x to a positive 7, which is another sign change. So, I have two sign changes here. So that means we're going to have possible negative, and we'll say real negative zeros, is going to be either 2, because there's 2 sign changes, or that decreases by an even quantity. So if I decrease this by an even quantity, the only even quantity I can decrease it by is 2, which would give me 0. Now, if you think about this for a minute, this polynomial f of x has the possibility of having 4 zeros, because again, our degree is equal to 4. And if you think back on the previous slide, we said there could be either 2 or 0 positive zeros, and we could have 2 or 0 negative zeros. So on the next slide, I'm going to go ahead and graph this and just kind of look at what actually happens on the graph of the function. Okay, so looking at our graph of our function, this is the graph I produced in Desmos, and if you look at this, if you look at the negative side here, we do not have any negative zeros. So we'll say there's no negative zeros because, again, the graph does not cross the x-axis on the negative side. So right here we don't have any negative zeros. And over on the right side, we have 2 positive zeros. One just past 1, and another one right about 4. So we can say that we have 2 positive zeros and no negative zeros. Now remember, from the Descartes rule of signs, we said there could either be 2 or none for positive zeros, and we also said there could be 2 or none for negative zeros. So just because our degree is 4 on our polynomial doesn't mean there's actually going to be 4 x-intercepts. In this case, we only had 2 x-intercepts, and they were both positive. Alright, it's time for you to check your understanding of Descartes' rule of signs. I would like you to describe the possible real zeros, both positive and negative, for the function g of x equals negative x cubed plus 8x squared minus 7x plus 9. You have 4 choices, A, B, C, and D. So go ahead and pause the video now, work out your solution, and select your response. Alright, so we are going to find the possible positive zeros. And if I count the number of sign changes in my equation, moving from negative to positive, that's 1 sign change. Positive to negative is a sign change. So that's 2 sign changes. And when I move from negative 7x to positive 9, that's a 3rd sign change. So it is possible that we have 3 positive zeros, or we can decrease that number by an even quantity. So an even quantity would be 2. So if I decrease that by 2, I could get 1. And for negative zeros, we have to evaluate this function for negative x and then count the sign changes. So g of negative x is going to be negative x cubed. This negative comes from in front of the x cubed term. Then I have plus 8 times negative x squared minus 7 times negative x plus 9. So a negative x cubed is negative x times negative x times negative x, which is negative x cubed, and then this minus sign out in front makes it positive. So I have x to the 3rd. And then here I get negative x squared. So negative x times negative x is positive x squared times 8 is a positive 8x squared. Negative 7 times negative x is positive 7x. And then a plus 9 at the end. Now if you look at this, all of the terms are positive here. So there are no sign changes. What that means is that there aren't any possible negative zeros. because there are no sign variations in our equation once we've evaluated for negative x, we will not have any possible negative zeros. So if you look at this polynomial, there could be up to 3 zeros. And it looks like based on our response, if it does have any zeros, they will all be positive. Now, our answer here, 3 or 1 possible positive zeros and no possible negative zeros, gives us a response to the multiple choice question of B. Now, you can always go and graph g of x if you want. You don't have to, but you can always go graph and look and see what actually happens, how many zeros it has, and like I said before, they're all going to be positive because it's not possible for this function to have any negative zeros. Alright, we're moving on to the fundamental theorem of algebra. The fundamental theorem of algebra states that a polynomial function of degree n, so its highest exponent, where n is greater than 0, has at least one zero that's real or imaginary in the complex number system. So we have, what it's saying is a polynomial function, as long as your degree n is greater than 0, always has at least one zero, either real or imaginary, in the complex number system. And the complex number system, you guys learned about complex numbers last year, like a plus bi is a complex number, or even just bi. To give you some examples here, like 3 plus 2i is a complex number, negative 2i is a complex number. I is an imaginary number that can also be written in complex form. So those are just some examples of imaginary zeros of a polynomial function. The corollary to this is that a polynomial function of degree n has exactly n zeros. So the number of zeros n is exactly equal to its degree, including repeated zeros, so those zeros that are repeats, or a function that has a zero that has a multiplicity or a multiple, and in the complex number system. So what we're looking at here is finding all the zeros of a polynomial function, not just the ones that we see on the graph that are real, but also finding those that are imaginary. Now, to piggyback off the fundamental theorem of algebra is the linear factorization theorem. And in this theorem, it states that a polynomial function f of x, when its degree is greater than 0, then f has exactly n linear factors. So if your degree of your polynomial is 3, it's going to have 3 linear factors. If your polynomial has a degree of 6, then there's going to be 6 factors in your factorization when you factor it all out. So, f of x is equal to a sub n, which is a coefficient, and then you have x minus c1, x minus c2, x minus cn. So you might have n, you are going to have exactly n linear factors for a polynomial whose degree is n. Again, a sub n is some non-zero real number, and c1, c2, c through cn are the complex zeros, including real zeros of the function. Alright, so I think we're going to go ahead and move on to an example here. I will reiterate this. If this linear factorization and fundamental theorem of algebra are not making sense to you right now, don't worry. I'm going to reiterate all this stuff that we just talked about in the next example. Okay, so what we're going to do is we're going to find a polynomial function given its zeros. It says write a polynomial function of least degree with real coefficients in standard form that has zeros at -1, 2, and 2 minus I. Now, so what we know is that x equals -1 is a 0, x equals +2 is a 0, and x equals 2 minus I is a 0 of the polynomial. And one thing with complex zeros is they always come in conjugate pairs. So 2 minus I is a complex zero because it's part real, 2 is a real number, and it's part imaginary. And when we combine the imaginary part with the real part, 2 and I, and separate them by either addition or subtraction, that makes a complex number. So the cool thing, I guess, about complex numbers, or complex zeros for that matter, is that they come in conjugate pairs. Imaginary and complex zeros always come in pairs of 2. So if you have a 2 minus I as a complex zero, then 2 plus I, its conjugate, okay? The word conjugate just basically means change the sign in the middle of the two terms. So 2 plus I is the conjugate of 2 minus I, and so both of those are zeros of the function. Now, based on how many zeros I have here, I already know that we are going to have a degree 4 polynomial. We're going to have a quartic polynomial when we figure out what the equation is. How do I know that? Because I have 1, 2, 3, 4 zeros, and the number of zeros of a polynomial function is always equal to its degree. Now, that is what the fundamental theorem of algebra states. Now, the linear factorization concept that we were just talking about on the previous slide states that that degree of 4 is also equal to the number of linear factors. So, if I know that x minus 1 is a 0, then x plus 1 is a factor of that polynomial. Again, because if I set x plus 1 equal to 0, what would my 0 be? If I set x plus 1 equal to 0, then x equals negative 1. And for x equals 2, my factor is going to be x minus 2. For the same reason, if I set x minus 2 equal to 0, x equals 2. Now, the conjugate or the complex zeros are a little different. When I write their factor, I'm going to say x minus 2 minus I. Because there's two terms here for my 0, I have to say x minus both of those terms. And what I need to do is put that, I need to put the complex 0 in another set of parentheses. And for the fourth 0, I'm going to state x minus 2. Sorry, I meant to say plus, not a t. 2 plus I. Alright? And what we're going to do here is we have 4 factors. 1, 2, 3, 4. There's a factor for every 0 in our polynomial. So that's the linear factorization concept that we were talking about on the previous slide. Now, my goal here is to figure out what the function f of x looks like. And to do that, I need to take all 4 of these factors and multiply them together to get my polynomial function. And I'm going to do that. Obviously, I don't have enough room here, so I'm going to do that on the next slide. Alright, so we are going to find a polynomial function here. And I think the easiest part for you guys to do will be to multiply the first 2 factors together. So I have an x plus 1 times an x minus 2. And to multiply them together, I'm going to FOIL. So if I multiply x times x, I get x squared. That's my first term. X times negative 2. My outer terms are going to give me negative 2x. 1 times x is 1x. And a 1 times negative 2 is negative 2. And I get x squared minus x minus 2. And that is part of my answer. Now the other part is found by multiplying these two factors together. But before I do that, I'm going to distribute the negative inside the parentheses. So I get x minus 2 plus I. And in the second factor, when I distribute the negative, I get x minus 2 minus I. And to multiply these two things together, first I'm going to distribute the x to everything, which gives me x squared minus 2x minus xi. And if I multiply the negative 2 to everything, I get negative 2x plus 4 plus 2i. And when I multiply the I times everything, I times negative 2 and I times negative I get plus xi minus 2i minus I squared. Now if you look at this, there's going to be some things that cancel out. We're going to have a negative xi and a positive xi cancel out. We're going to have a negative 2i and a positive 2i cancel out. And this negative I squared is equal to negative 1. So if I substitute negative 1 for I squared, and I have a minus sign in front of it, it's minus I squared, then is going to be minus a negative 1, which is a positive 1. So moving forward, I get x squared minus x minus 2. And times, in this set of parentheses over here, we get x squared minus 2x. Oops. I can combine some like terms there. Minus 4x, because the negative 2x and negative 2x could get combined. And I'm going to get a plus 5 at the end, because this is a positive 4. And remember, this negative I squared is a minus a negative 1, which is positive 1. So 4 plus 1 is 5. Now, I'm going to multiply out these two trinomials on the next slide, and then I'm going to have my polynomial function. Alright, so I'm going to distribute the x squared to every term in the second set of parentheses, which gives me x to the fourth minus 4x cubed plus 5x squared. I'm going to distribute the negative x, which is negative x cubed plus 4x squared minus 5x. And when I distribute the negative 2, I'm going to get negative 2x squared plus 8x minus 10. So if I combine like terms in this polynomial, x to the fourth is my only degree 4 term. I have negative 4x cubed and negative x cubed, which gives me negative 5x cubed. Cross those off because I combined them already. Then x squared terms, I get 5x squared plus 4x squared, 9x squared. And subtract 2 is going to give me 7x squared. So I'll cross those off because I combined them. And negative 5x and positive 8x gives me a positive 3x. And then obviously the constant is negative 10. So this is the function, the polynomial function, we'll call it f of x, that has zeros that were given to us at the beginning of the problem. Alright, so it's time for you to check your understanding. I would like you to write a polynomial function of least degree with real coefficients in standard form that has a negative 2 of a multiplicity of 2, 0, and 3i as zeros. Okay, so just so you guys know, reminder that multiplicity of 2 means that negative 2 occurs twice. And you have 0, and 3i. And remember also that imaginary or complex zeros come in conjugate pairs. So even though they don't tell you this, if you have 3i as a 0, then negative 3i is also a 0. Alright, so just looking at this function, or looking at the zeros, you might be able to look at this multiple choice question and narrow down your choices by eliminating some answers. But go ahead and work out this question and choose a response A, B, C, or D. Alright, so we're going to work out this problem. We will have factors at x plus 2 and x plus 2, again because our multiplicity is 2. We'll have one at x equals 0, which means we have a factor of x. And we have a factor of 3i and negative 3i. And I didn't write that in factored form. My bad. It should be x plus 3i and x minus 3i. Now, what we're looking for is to multiply this stuff together. So I'm going to first start by multiplying x plus 2 times x plus 2. That gives me x squared plus 4x plus 4 if I FOIL. Then I'm going to multiply that by x. If I multiply these two together, I get x cubed plus 4x squared plus 4x. And if I FOIL out the two complex factors, or the ones that produce zeros at 3i and negative 3i, I get x squared minus 3xi plus 3xi minus 9i squared. So first, outer, inner, inner, and last give me this expression. So the negative 3xi and the positive 3xi cancel. I squared is the equivalent of negative 1. So I end up with x squared plus 9. And when I multiply that by x cubed plus 4x squared plus 4x, I'm going to start by distributing the x squared to everything and get x to the 5th plus 4x to the 4th plus 4x squared. And if I distribute, I take that back. I meant to say x cubed here. 4x times x squared is 4x cubed. And then if I distribute the 9 to everything, I get 9x cubed plus 36x squared plus 36x. And when I combine like terms, the cubic terms here can be combined, which is 13x to the 3rd. So I'll get x to the 5th plus 4x to the 4th plus 13x cubed plus 36x squared plus 36x. Which tells me that the appropriate response to the multiple choice question was D.